78% nitrogen, 21% oxygen.
1% carbon.
You're going to get a car one of these days and you're going to go to the your mechanic and like, we're doing something special for you. We're filling up your tires with nitrogen. And they do this, and they put a little green cap on your tire. And I laugh. They're filling up the car with the tires with nitrogen. The atmosphere is already 78% nitrogen. They're not doing you very many favors here. Okay? And nitrogen and oxygen are very similar. Guys, I need you to pay attention to this. Okay? So nitrogen, 78%. Plants use this, animals use this, you use this, you breathe it in, you get all kinds of cool amino acids and things in your body. But what we really like in the atmosphere is oxygen. Other planets have nitrogen. Other planets have carbon dioxide. Other planets have methane. But nobody's got oxygen.
Like wheat beer?
Yes. We are the only planet, excuse me, that has oxygen. And that is super cool, because you can't live without oxygen. Life as we know it does not exist without oxygen in the atmosphere. So, carbon dioxide we have, but you notice these are percentages, how small this is. Argon, we have more argon than carbon dioxide. So, very, very small amount of carbon dioxide, as opposed to the planet Venus, which has got like 99% carbon dioxide. Okay. I believe this is the answer to number 3 in your notes. Number 3. Now, we did not always have this really happy living atmosphere. Wait, please. You taking notes? Okay. We did not always have this happy atmosphere. What we used to have was carbon dioxide, carbon monoxide, and water vapor. Now, if I ask you, if I give you a statement, the ancient atmosphere used to have this, this, and this, your first response to that should be, how do you know that?
How do you know that?
Good question. Okay, the first thing, the first kind of piece of this puzzle in understanding how do we know what the ancient atmosphere had, well, I'm going to tell you one thing. I wasn't there, I didn't see it. And a lot of geology is looking at the effect of things on other things, and we can kind of go backward in a cause and effect and see what actually happened. That's geology. First thing, the present is the key to the past. If it happens today in a certain way, it's always happened that way. There's no reason to think it hasn't happened any differently. For example, volcanoes erupt. We've learned about volcanoes. They spew out all kinds of gases. Well, guess what they spew out in large quantities? Water vapor, carbon monoxide, carbon dioxide. I think one of the times I checked a number, one volcano erupted, I think 70% of the gases that came out of the volcano was water, just water vapor. A lot of carbon dioxide, a lot of carbon monoxide, and some other nasty things as well, like sulfur dioxide.
It was very hot water, right?
Was that?
It was very hot water, right?
It'd be water vapor.
Oh. It's like steam?
Okay.
Yeah, really?
Steam is actually condensed water vapor, and that's what you see as steam. Okay. Now, so, thus, first thing, how do we know what the ancient atmosphere was? Well, we see where we get gas today. Where do we get gas today? From inside the Earth. So, I think that's even an answer on your study guide there, is where do we get this ancient atmosphere? What does it come from? Your answer is?
Yes,
The gases that erupted from volcanoes.
Stay awake. Y'all, enjoy yourself. Okay. Second thing, how do we know? How do we know? Banded iron formations. Banded iron formations are also known as BIFs. Banded iron formations. So here's a banded iron formation. We can have bands of iron and other things. Bands of iron. We're going to go with that. Now, the trick to a banded iron formation is very simple. How does this help us know that there was no oxygen in the atmosphere?
They can only be made if there's no oxygen.
They can only be made in an anaerobic environment. If there was oxygen in the atmosphere when the banded iron formation was being made, it would have turned into something else. It wouldn't have been a banded iron formation, it would have been something else. So just the very fact that we have banded iron formations tells us, wait a second, the only way this could have formed is if there was no oxygen. So thus, there was a time when the planet had no oxygen. That's what we learned from banded iron formations. That's part one. Okay? What's part two? Part two. Now, stromatolite formations. We learned something from these rocks that we call stromatolites. It's like mixing the word stromboli and tomato. Stromatolite. Quiet, guys. Now, stromatolite is formed by a little creature called a cyanobacteria. Okay? Cyanobacteria, Dejan, to kind of help you here. This does the same process you get with eutrophication. Okay? Now, cyanobacteria, blue-green algae. Wait, cyan. Is anyone in here wearing the color cyan today?
No.
Now, Trent's kind of close with this shirt, but cyan is a blue-green color. Okay, so a cyanobacteria is a blue-green algae. Now, they form these cabbage-like formations. In fact, I was approached by a gentleman from a publishing company, and he asked me, can I use your picture in our new college textbook that we're putting in? And I said, yes you may, I'll take that $100. So, there you go. This is Professor Callan Bentley. He is, I believe he's the associate professor or assistant professor of geology at Northern Virginia Community College, Annandale. He is an amazing professor. If you want to know science and geology, he makes it a lot of fun. This was a field trip that we went on, a field trip class. It was a class that was a field trip to the Northern Rocky Mountains. For 10 days, we went from site to site to site, actually learning geology in the field. It was a lot of fun. He was standing on these stromatolites and actually teaching us about these stromatolites. Now these stromatolites, well, here we have stromatolites. And these stromatolites are these beds of algae, and they grow in these little small circular domes. Now these small circular domes of cyanobacteria bring in and convert carbon dioxide plus a little bit of water plus a little bit of sunlight. What does it make? It makes oxygen. Okay? And energy. Well, energy in the form of cellulose or sugar. Okay, what is this process called? Photosynthesis.
I was going to say that.
Now, cyanobacteria. The cool thing about photosynthesis, as far as these guys go, is some of the carbon gets converted into a rock formation. And as they start to grow, they grow like coral grow. Where coral is a little organism that secretes the coral reef underneath it. The cyanobacteria secrete the stromatolite under it. So that's what a stromatolite is. But I'm telling you, how do we know part two? And this is how do we know what the original atmosphere was? We find stromatolite formations across the globe, all from a certain time period. What does that tell us? Wait a second. All of these stromatolites everywhere were processing the carbon dioxide and water out of the atmosphere and turning it into rock. And they were capturing the carbon dioxide and that carbon dioxide gets captured as rock. So one, carbon dioxide is leaving, and what is showing up? Oxygen. So what do we owe our early atmosphere to? Cyanobacteria, making those stromatolite formations. So if you go to Glacier National Park in Montana, you can see these stromatolites everywhere. They're all over the place. Okay, if you go up to the top of Grinnell Glacier, there's stromatolites that, like as big as this quad of desks. Just one. They're really big up there and really cool. Okay, so those are the two of the things that of why we think we had a different atmosphere. Just two. Okay, you guys good with that?
Yes.
Okay. Sinks! We gotta talk about some sinks. Now, I'm not talking about washing your hands in the sink. I'm talking about a sink as a storage of an element. Storage of an element. For example, if I wanted to store oxygen inside the earth, where would I store it? Well, one of the places you could store it would be in a banded iron formation. The banded iron formations are made of these ferric oxides. Ferric, Fe meaning iron. Okay, so magnetite and hematite, these banded iron formations have quite a bit of oxygen locked away and bonded to the iron. We cannot access this oxygen. We cannot breathe it. I'd like to see you go up to a steel car and try to breathe it. It's not going to work. It might be funny, yes, but it's not going to work. Okay, another place that oxygen is locked away is in the water. What is water? What's the chemical formula for water? Yeah, dihydrogen monoxide. Okay. There is a lot of water on the planet. 70% of the planet is ocean. These oceans are pretty deep. There's a lot of water, and that water has hydrogen bonded to the oxygen in a very tight way, and you can't get to it. Okay. Now we move ourselves down a little bit here. So, carbon dioxide. Guys, we often talk about where do we find carbon dioxide, or I'm going to refine this a little bit further down. Instead of carbon dioxide, where do we find carbon locked away? Well, the first place that we find carbon locked away is in the ocean. Now, does anyone in here have a soda?
Okay. Had a soda.
Had a soda. Let me see the bottle. Okay, I'm going to read you the ingredients on the bottle. Carbonated water. First ingredient. So if you shake a soda up and then you pop it, what usually happens? It explodes. What's causing the explosion?
The caulk.
The carbonation that's under pressure trying to escape. So what does that tell you? Can water dissolve and hold carbon? Yes, it can. So, ocean water becomes a sink for carbon. Because all of this carbon, or I should say, all the carbon in the atmosphere freely exchanges in and out with the ocean water, usually in the waves and where the ocean is being broken. Okay? So, ocean water holds a vast amount of carbon dioxide. Okay? There's two other sinks that right here. Okay, a carbonate rock layer. Carbonate rock layer has a lot of carbon in it. Limestone. You also have all these fossil fuels that we're burning. We learned this in the resources unit. All these fossil fuels that we're burning are releasing what gas? Carbon dioxide. So fossil fuels, coal and oils are also sinks for carbon. Okay? Okay? There are three ways that heat can travel. It can travel in any direction from the sun. It moves to the earth quick as a shadow and disperses in radiation, conduction, convection. Okay? Time to show you a video.
Oh.
Oh,
Yeah.
oh, why you do
So I haven't heard this
Today we are going to look at the different types of energy transfer: conduction, convection, and radiation. We will first start with conduction. Let's take a look at a picture that represents conduction. What do you think conduction means, just by looking at this picture?
So if we look at conduction, the pot's being heated, and then you think the spoon's going to get hot? Yes. that's
Conduction is a transfer of heat or thermal energy by touching. It occurs in solids. It is a transfer of heat from the warmer part of an object to the cooler part of the same object. For example, if you have a pot that is on the stove, it's going to get hot on the surface that's touching the burner, and that will continue to move to the cooler part of the pot that is up at the top. It can also be transferred from a hotter object to a cooler object. Refer back to the picture. On the picture, the metal spoon was leaning up against the metal pot. That metal spoon will become hot because that heat will be transferred from the hot pot to the cold spoon. The next type of energy transfer we're going to look at is convection. Take a look at this picture. What do you think convection means? All right. Convection, unlike conduction, occurs in liquids and gases. It is the transfer of heat through the movement of particles. Warm particles rise, cool particles fill in the space below. So this is a circular motion. Think about a house. Have you ever noticed that maybe upstairs or in an attic it gets warmer? That's because the warm air rises, and it's usually colder downstairs. All right, the third energy transfer we're going to discuss is radiation. Take a look at the picture and decide what you think radiation means. It is a transfer of energy as waves, and it travels through matter or empty space. So radiation, what we usually think about is the sun. The earth is warm because the rays from the sun are traveling through matter and casting the heat to the earth. So let's take a look at one more picture. This picture demonstrates all three forms of energy transfer. Right now, I want you to take a moment to look at this picture and explain how conduction, convection, and radiation are demonstrated in the visualization.
What do we got? What's the fire doing? Yeah, it's radiating heat. Radiating heat. It's sending out those heat waves. As you get closer to a campfire, you can just feel it. Feel the energy as it's on you. If you're out in the sunshine, a certain temperature of the day, it doesn't matter what temperature it is, but if you're in the sun, you always feel warmer because you can feel the radiant energy heating your skin. Okay? So that's radiation. As the fire here starts to heat the pot up, what does that do to the water? Put your phones away, guys. What does that do to the water? It heats it. Okay, what does that do to the density of the water? It becomes less dense. Less dense stuff rises, then it cools, and it get this convection cycle, or moving particles of water. Get this, stuff always goes from warm to cold. It does not go from cold to warm. It always goes from warmer areas to colder areas. And lastly, we have conduction, or through the pot, it's going from the warm part of the pot to the cold part of the pot. Do you guys ever notice how a lot of cooking utensils have wood handles or rubber handles? Why do they have wood or rubber handles?
So you won't burn your hand.
Why would you burn your hand, Mary?
Because of the Like, I don't know how to explain it.
Then you would say something like the heat is traveling through the pan to the handle.
There it goes.
Okay, from the warm part of the handle to the cold part of the handle. It's actually traveling through. Okay? Got another video. Okay. Oh, come on, today's like a video day. All these little videos are fun.
There are three ways that heat can travel, but it can travel in any direction. From the sun it moves to the earth quick as a shadow and disperses with radiation, conduction, and convection. There are three ways that heat can travel, but it can travel in any direction. From the sun it moves to the earth quick as a shadow and disperses with radiation, conduction, and convection. First things first, let's discuss heat. What it is before you pay for it to warm your feet. Heat is the energy that flows when atoms and molecules move. It diffuses out towards coolness. Temperature is the measurement of the average motion of these atoms and molecules in the atmosphere. So there you have it. Now the first way of transportation of heat energy is radiation, like sound waves from your radio stations filling the empty space around you. Your radiator warms you, but don't start a fire now, I warned you. Heat is going through radiation from the sun before it burns you. From 93 million miles away to re-radiate this heat is what the earth does for you. This is survival, what this heat is going through before it rises to the sky and it's gone. So there are three ways that heat can travel, but it can travel in any direction. From the sun it moves to the earth quick as a shadow and disperses with radiation, conduction, and convection. There are three ways that heat can travel, but it can travel in any direction. From the sun it moves to the earth quick as a shadow and disperses with radiation, conduction, and convection. Conduction, the second method on my list. You can feel it like a hot pie in your fist with the handle gripped. I bet you'd rather grab a candle lit, cause it's heat through conduction that causes this. Atoms and matter in a fixed position vibrate when heated like a pan in the kitchen. Transmit the heat energy to atoms next to them that are cooler than they are, to cause equilibrium. To even out the temperature the heat has to travel. Up the spoon in your tea in the morning with your bagel. It might burn your hand, but just learn the land of conduction, heat energy until you understand. The earth gains little from conduction. It's mostly radiation that helps us function and keeps us warm. It's just another way for heat to move. But now let's move on to method 3 to prove. There are three ways that heat can travel, but it can travel in any direction. From the sun it moves to the earth quick as a shadow and disperses with radiation, conduction, and convection. There are three ways that heat can travel, but it can travel in any direction. From the sun it moves to the earth quick as a shadow and disperses with radiation, conduction, and convection. Convection is the movement of heat in liquids and gases to even out the temperature fastest. This process is called diffusion. It's a flow of particles cold and hot in a fluid. If you're not listening, then stop what you're doing, cause this is the final mode that heat can move in. And this affects you every day. It's the breeze at your back and the wind at your face. When heat reaches the earth, it rises at a rate with the air in the place, and it moves up till it cools. Trillions of molecules together make up the weather that we see on the news. It's how they measure the pressure of the air and the temperature, but convection is how it got there in the atmosphere. So don't be scared. Heat moves in three ways, so we make things clear. It's like there are three ways that heat can travel, but it can travel in any direction. From the sun it moves to the earth quick as a shadow and disperses with radiation, conduction, and convection. There are three ways that heat can travel, but it can travel in any direction. From the sun it moves to the earth quick as a shadow and disperses with radiation, conduction, and convection.
She liked it. That was good. Making a song about it. That's talent.
What do you say? I don't know, you said something that made me mad. I said, you know, I ain't. You said something. I don't know. I don't have my phone. I bet you got my number. So you can kick me, so I don't kick me.
Okay. So that's energy transfer. Did you guys get that? You understand it now?
You know, say it about me.
Pick up train.
Take notes of this.
Okay. Let's talk about the greenhouse effect. Alright, greenhouse effect. All this really good stuff today. Okay, so you guys are going to the store, you're going to buy some groceries. You go into the store, and it's Walmart, so it sucks you in for 2 hours. And by the time you finally escape from the hellhole of Walmart, you get out in your car, you open the door. Now it's been, 35, 40 degrees outside, but the sun is really shining. And you open the door, what do you feel? Heat. Why do you feel so hot?
Because your sun is. Are you talking about when your car is parked, so like you're just
Okay.
Wait, and the sun was shining on it?
Okay, what happened to me is I actually, this weekend, it was starting to get kind of chilly. Went to the farm where I have my horses, parked my car there. We were there for about 2 hours, and when we went to leave, I opened the door, and even though it was really chilly outside, I opened the door and the sun was shining the whole time. I had to vent the car out because the car was so hot. What caused my car to get so hot? The sun's rays go into the car and heat the car up. But it doesn't allow, the glass enclosure doesn't allow the heat to escape. That's called the greenhouse effect. Now that can happen in a car, that can happen in a glass house, a sunroom, it can happen in your bedroom. Okay? But on the earth, instead of having glass, what we have to keep us warm is carbon dioxide, nitrous oxide, methane, and a couple other gases. Specifically water. Water's a really good greenhouse gas. These greenhouse gases, Deja, what they do is they keep the earth from freezing. So, besides you need to know the fact that Venus has a runaway greenhouse effect, I have another video for you where you get to see a guy get punched.
Mike Tyson.
No, not Mike Tyson. Okay, here we go. Let's try this again.
Yes or no?
Very, very bad. Very, very bad.
Wow.
You bad human. Do you know why you were punched in the face? Okay, let me tell you. You were punished because you are causing global warming. Do you know what global warming is? But first, clean your tears. Take this hanky. To understand global warming, you first need to understand the greenhouse effect. Do you know about the greenhouse effect? Oh, you're thinking about a house which is green. Don't act like a stupid. There are a few gases in atmosphere, like carbon dioxide, methane, nitrous oxide. These are called greenhouse gases. These greenhouse gases are good if they are in right quantity. These greenhouse gases form a layer around Earth. When rays of sun come and fall on Earth, some of them are absorbed by Earth, but most of them reflect back to the atmosphere. These reflected rays reach upper atmosphere. There, greenhouse gases take most of the heat from these rays. Some of the heat goes into space. The heat captured by greenhouse gases spreads in every direction. These heat, which has been trapped by greenhouse gases, helps to keep our Earth warm. If heat of sun is not stopped by these greenhouse gases, our Earth would freeze and average temperature would be 18 degrees Celsius. So these gases are good for Earth's survival. Otherwise, plants, animals, and we humans would have no life here. This stopping of sun heat to keep Earth warm is called greenhouse effect. So greenhouse gases are good. They trap the heat, So they help Earth to have nice temperature so that we all can live here happily. Do you know what we humans are doing? We are increasing the amount of these greenhouse gases. We have smoke coming out of vehicles, smoke coming out of factories. In this smoke, there is a lot of methane, a lot of carbon dioxide, which are greenhouse gases. Also, do you know trees and plants breathe in carbon dioxide gas, thus reducing it from atmosphere and keeping a balance of greenhouse gases? But unfortunately, we are cutting trees too, so there are less plants to absorb greenhouse gases, but more cars and factories to increase these gases. When these greenhouse gases become more and more in atmosphere, the layer of these gases become more and more thick. So when some rays come down and get reflected back by Earth, they reach this thick layer of greenhouse gases. All these heat rays get trapped, nothing goes up into space. Temperature is increasing, Earth is becoming warmer. This is called global warming. So, now you know why you got punched. You, like all of us, are also responsible for global warming. Oh, it is too hot today. Good, you...
Okay? Does that explain greenhouse effect pretty well? I thought so. There is a planet in our solar system that has like crazy greenhouse effect. That's Venus. Venus's atmosphere is super, super thick. And it's made of carbon dioxide. So it's entirely greenhouse gas. And, well, it gets so hot on the planet Venus that it will literally melt your car. If you had one there. We landed a probe on Venus and it melted. Okay? Kind of a bad thing. Okay? Okay. This is my last slide of the day. So we didn't have a lot to talk about today. But, volcanoes. Volcanoes. What about volcanoes? Well, I said earlier that we get most of our atmosphere originally from volcanoes, right? And they're putting out a lot of carbon dioxide, right? So if we have all these volcanoes erupting, is that causing all the global warming? Not really. Really what the volcanoes do is, yeah, they put out carbon dioxide, yeah, they put out some methane and some other sulfur dioxide, nitrous oxide, some other things. But mostly what these volcanoes put out is ash and dust. Volcanoes and actually meteor strikes too. So all this ash and dust gets into the upper stratosphere. This upper stratosphere ash and dust cloud, well, it blocks the sunlight. The less sunlight that hits the Earth, the colder it gets. So volcanoes, instead of causing global warming, if it's a really, really bad eruption, it actually causes global cooling temporarily, at least until the ash disappears. Okay? An example of this, in 1815, Mount Tambora in Indonesia had a massive eruption. It put so much ash and dust into the atmosphere, and this is in Indonesia, south of the equator, I believe, that summer was not summer. That summer was winter. You know how it keeps snowing? We keep having like, ooh, 60 degrees, snow. 60 degrees, snow. That's what this year has been like. It's supposed to snow next week again. Okay, so the year of 1815 was called the year without a summer because it was snowing in June. Okay, they had snow and winter conditions for over a year. Now imagine how bad that would be. It snows all summer long, and then winter comes again and it keeps snowing some more. That would be the worst year ever. You know, if I want no seasons, I want to be in the tropics where it's like nice and beautiful all the time, not snowy all year round. Okay, I feel like some new version of the story Frozen. Okay. Okay, so, do you guys have any questions about atmosphere stuff?